All right, cool. So we're going to start this. This is the evening slot, so we're going to start with a little bit of evening gymnastics, I thought. So hands up if if you have, including this one, ever been to Java 1 before. Come on, including this one, who's been to Java 1 before? All right, every hand should be raised. Cool. Who in here has heard of NoSQL? Hands up. Cool. Who here has heard of SQL? All right, we're learning. Who here has used a so-called NoSQL database? Hands up. Keep your hands raised if you've also used a graph database. Cool. Keep your hands raised if you used Neo4j. Yay! Awesome. Fantastic. Cool. So my name is Emil Eifrem, and I'm the CEO of a company called Neo Technology. We're the commercial sponsor of an open source project called Neo4j, Neo4j, which is right here on my shirt, which is an open source graph database implementation. It's also a product, also ironically called Neo4j, which is the most popular graph database out there today. I'm going to talk for the remaining 58 or so minutes about graph database use cases that are not social. Right? So graph databases is in this kind of interesting spot now where it's actually starting to become fairly known amongst developers, but a lot of people peg it to be exclusively for social, which is, it's one of those dangerous types of truths, right? In that it actually is true. It is very, very useful for social data, but it's not exclusively useful for social data. So I'm going to be outlining a couple of thoughts along those lines for the remainder of this talk. Please keep this as interactive as possible. It's a fairly small group, so just raise your hand if you have any questions. And do tweet about this as well, please. The conference network seems to be working better this year than previous years, so that's good. Maybe not perfect yet. All I ask is that you use the Neo4j hashtag Neo4j, because we monitor those tweets religiously. I have a super simple agenda today. 1, 2, 3. The first one is we're going to set some context and talk about where we are from a graph database perspective. And then I'm going to take a step back and just establish 101. There's probably 40-45% here who haven't used a graph database. And talk about what graphs are actually, foundationally. And then we're going to get into the use cases, specifically the use cases that aren't social. So, a word of warning though, we are at, I guess, Oracle Open World these days or something like that. So it's a lawyer-sponsored conference, right? So I'm going to get my liabilities up front. I can't offer anything in this talk except for the truth. I've given variants of this talk for a while now, and there are some victims. For example, this gentleman, an Indian gentleman who watched, I'm not sure if you guys can see this from the back, but he watched the photographs from his Diwali fireworks, and he says he's seeing graphs everywhere. So he's looking at the stars in the sky and he's seeing graphs. Hands up, how many are seeing graphs in that photo? Okay, not a single one. Let's see, I'm going to show this again after this talk and we'll see how we're doing. Another victim saw this talk or a similar one and went home and then looked at his curtains, and it's like, graphs are everywhere. So context, we're going to be talking about graph databases, but before that, let's keep this interactive. I want to ask you a question. So what is the one thing that all 5 of these companies, 1, 2, 3, 4, 5, 6, all 6 of these companies have in common? Can I get some suggestions? Make a ton of money. Good one. Consumer focused. Good one. Third time's the charm. What's that? Contact management? I don't understand that, but maybe that's true. Massive number of users. All good ones. So I'm going to argue that actually the key thing, and I'm sure all of those are true as well, but the one that I have top of my mind is that actually the secret sauce for every one of these companies, why they ended up winning their market, is one key thing, is the fact that they took a look at their data and they did not just treat it as silos. But they said that, hey, there's connections in our data, and if we start leveraging those connections, that can unlock a lot of value. And I'm going to give you a bunch of examples about this, and I'm going to argue that this is a trend These are all consumer web companies, but that this is a trend that started out in consumer web, but is now spreading completely horizontally across other verticals. We call this trend sort of tongue-in-cheek, graphs are eating the world. Graphs are eating the world. Vertical after vertical are being consumed by graphs. And I'm going to be walking you through how our thinking around that. So the first example out of the previous slide is that of web search, right? So if you scroll back a few years, 15 or so years, back to the end of the 90s, there were 50 search engines out there, 50 search engines. Everyone knew that search was dead. There was no innovation left in search. And they all did this absolutely amazing thing. I remember even back in those days, 15 years ago, I thought about that and was like, holy shit, this is awesome technology. Because what they're doing is basically, let's crawl the entire web, every single document on the web. Let's download that into our data center. Let's index that and look into that. So when you're searching for water, we're going to look inside of each and every one of these documents. Sure, indexed, I'm sure B+ trees and all those good things, but conceptually, order one, look inside of each and every one of these documents and see the documents that have water in them, serve the result back, right? And oh, by the way, we're not going to just do this once. No, we're going to do this every day from now until perpetuity. Like I just thought that technology was amazingly amazing in its ambition. They all did the same thing, but then along comes a small startup which does exactly the same thing as the other guys, but they also do that. They also do basically they say that, hey, you know what? Let's not look at these as single documents, but let's look inside of the HTML and see that, hey, there's an ahref in here. Let's extract that. Let's say that's a link, which of course those of us who know HTML know that's a link, right? And then extract that into a connected data set and then rank the search results. Don't just return all the documents that have water in them, but let's rank the search results along the connected data sets. Let's use one link as a vote. Use that algorithm that they called creativity PageRank, which actually was not named after the pages that they crawl, but after one of the inventors, Larry Page, right? And of course, this startup was Google. We've all heard about PageRank, and that's the key innovation. That's the reason that this company is probably the most formative and defining company of at least the previous decade, and all of these other companies are gone, right? One single innovation, the fact that they looked at their data and said that connections in data are really, really valuable. Next example, in recruiting, Monster.com, very big, very famous, still around today, and they do online job search, job ads basically. They help people find a job, and how? Well, basically the standard way, which is let's look at job profiles and let's match them to CVs. And if we have a good match here, let's return that as a good search result, right? And then along comes another company called LinkedIn. And they say that no, actually, the way that human beings have always found jobs or occupations is through their connections, through the social graph, through their network of people that they know. And they built a product that enticed people to volunteer the connections that existed already in the physical, real world. They digitalized them, and they built an infrastructure that allowed them to process these and then completely dominate that market. Same difference here. In this space versus in Google Alta Vista. Another example, more subtle, is that end of 90s, early 2000s, a lot of people tried to do online payments. And one company pulled it off, one company only. And that company was called PayPal. And I spent some amount of time thinking about connections in data, but I actually didn't realize this myself, that the key reason that these guys were successful is that they managed to build an infrastructure that allowed them to handle connections in data really well. Because the key risk to doing online payments is fraud. And it turns out that when you're looking for fraud, if you have only a view of isolated transactions, the Citibank, for example, where they saw one transaction, one transmitter, one receiver, or if you have the entire payment network, the payment graph, you can detect a lot more fraud and have much more precise algorithms if you see the entire connected data set. 3 examples, and they were all consumer web. What we're seeing inside of the graph database space, and this has changed just in the past couple of years, is that this trend started out in the consumer web, but it's now spreading across other verticals. When we started out a few years ago, actually started out quite a long time ago, but when we started raising venture capital, when you started getting investors in the company, that's when you need to start articulating the market for your product, right? we said basically, look, we have a hypothesis. We don't know yet. It's very early in the era of graph databases. So we don't know yet where ultimately the market is going to end up. But we have a hypothesis. And that hypothesis is that we have 3 verticals: web ISVs, so software companies, right? And then financial services and telecom. And we have 4 use cases: network and data center management, master data management, social, and then geo. And I'm going to be double-clicking on all of these later. And in this 4x3 matrix, we believe is going to be the early adopter market. And specifically only for Neo4j. I'm talking mostly here about graph databases in general, but all of my examples are from Neo4j because that's the one graph database that I know the best. Specifically for Neo4j, we now have a scorecard, right? Where did our customers end up coming? And you can see that this entire 4x3 matrix is now filled out, and this is a sample data set of the customers that are using Neo4j in production today. Super proud of this. You see big companies, HP, Cisco, etc., as well as small hyped ones like Snap Interactive and 53, etc. But we're even more proud what happened outside of this 4x3 matrix. Because in parallel to the adoption that we've seen inside of the early adopter market, there's been an explosion of graph database usage outside of a multitude of other verticals. And this is the trend that we call graphs are eating the world. Because what we are observing is that once one company in a specific vertical starts using a graph database, or at least starts exploring connections in their data and start leveraging them, they all of a sudden have a more fine and precise view of the world, and they're able to build much more powerful products. So all things being equal, which they never are, but all things being equal, that product will then be a better product than the product that only uses data in silos. And the Google to Alta Vista example comes to mind. And so after a while, this company will then either start completely dominating their market, or they're going to force other competitors to adopt graph databases as well. Graphs are eating the world. So we're not the only ones seeing this. These were all internal metrics, so our own customers that I see day to day. But there are some external data points as well that point to this. So there's a site called dbengines.com. Evening gymnastics again. dbeengines.com. Who has heard of dbeengines.com? Hands up. Only a few people. So basically it's a site that tracks a number of different signals. They track 150 database projects along the axis of how many people have added them as a skill on LinkedIn, how many tweets mention that specific database project, Google PageRank for them, Stack Overflow questions, etc. They have 7 or 8 different things that they measure. And then they compute a score. And what's interesting is that they not only compute a single discrete score per project, which actually is interesting in and of itself, but they also group them by category. And it turns out that graph databases have been the fastest growing category not in NoSQL, not in big data, but in databases for most of 2013 and all of 2014 so far. Which is kind of interesting. Graphs, let's not kid ourselves, is the least known of all of the so-called NoSQL databases by far. But it's been the fastest growing for quite some time now. So that's all fine and dandy. But if you have popularity, this is only popularity, and now analysts are starting to cover the space. And this is one example, Forrester, I'm sure you've heard of them. They now estimate that inside of the enterprise, more than 25% will be using graph databases in production by 2017. So there's a lot of evidence of sort of the traction in graph database. I'm not going to spend more time about this, although please ask me about this afterwards, because I'll be talking for hours and hours about it. But let's take a step back. What are we talking about here? What is the graph anyway? Right? So I'm actually going to take you way back to the 1700s, to the 18th century. And graphs actually started out in a small town back then called Königsberg, which is Kaliningrad today in Russia. And Königsberg or Kaliningrad is a city on both sides of a river called Pregel, which is the river you see here. the blue in this picture. And it consists of basically, it's on both sides of this river, but then it has two big islands. And those big islands are connected to the mainland and to the other island through 7 bridges. 7 bridges. And there's a very famous 7 bridges of Königsberg example, which gave birth to graphs. And basically those 7 bridges, if we remove, we'll have a more cleaned up map. You can here see the 1, 2, 3, 4, 5, 7 bridges between these different islands and through the islands to the mainland. And there was one guy, a gentleman called Euler, E-U-L-E-R, Euler, who for some reason wanted to answer the question, is there one way, well, at least one way that I can walk through Königsberg and pass all of these bridges once, but only once. Every single bridge once, but you can't go back and forth on one, so only once. Is there one path that you can do this, right? It turns out that it's not actually that easy to figure out the answer to that question. You can sort of intuitively do it. If you start tracing, you're going to see that I'm going to get into a dead end, right? I can't reverse back over a bridge. But intuitively, yeah, that's one thing, but how can you do it to mathematical rigor, right? And so what he ended up doing was that he said that, well, he thought about it for a while and came to a couple of conclusions. One of them was that it really doesn't matter how you're going to walk inside of every one of these land masses. You can just actually treat them as sort of indivisible atomic units. What really matters is how you walk across the bridges and in what sequence you do that. So he reformulated the problem using a new type of vocabulary, where he said, in modern terminology, is that we have 4 nodes, and between those nodes we have 4 edges or 4 relationships. And how can I walk through this graph, visiting multiple nodes, the same node multiple times, but the relationships only once. 2 abstractions, nodes, and relationships. And that was the birth of graph theory, which has ended up becoming one of the most important subdisciplines of mathematics. I'm sure many of you have amazingly fun memories of your college mathematics classes in graph theory. So the way this has evolved on the database side is that in databases today, there's a model that is called property graphs, which builds on the original abstractions as formulated by Euler, where he said that there are nodes and relationships, but in the property graph model, we also have key value pairs that you attach to both the nodes and to the relationships, right? So think of the nodes as basically a java.util.map, if you will, right? And the same thing with the relationships, but the relationships have a type. That ends up being important. It's important if I know you, or if I'm in love with you, or if I own this car, or if I drive this car. So the type of the relationship is important. And you can also add labels on top of the nodes. You can say that this node is a person node, or this node is a car node, as an example, right? So those are the key abstractions in the graph database. So if we take an example, right? Let's say that how would you query a graph database, right? So let's say that I'm going to New York and I want to find a restaurant in New York. I happen to like sushi. I go on to Facebook and I search for using their new graph search product, or new, it was launched last year, where I can type in sushi restaurants and it's going to sort of bolden the things that are nodes or entities. And sushi restaurants in New York. But not just any sushi restaurant in New York, but I want the restaurants that my friends like. So a very simple type of recommendation. It would look something like this, right? So basically we have me and I have 2 friends in this fictitious example. In real life I'm very popular and have many, many friends, especially with the ladies. They all love me. So I have 2 friends in this fictitious example, and they like a bunch of different things, but we've now extracted the ones that are located in New York and that serves sushi, right? So me, my friends, a subset of my friends who like things that are in New York and that serve sushi, right? So how would you express that? Actually, that was natural language, right? How would you express that in the graph query language? Well, there's one graph query language called Cypher, and I believe there's a talk about Cypher actually. When is it, Stefan? Tomorrow at 8, there's a talk specifically that talks about the internal of Cypher. So the way that you would express this in this graph query language is maybe counterintuitive at first. So what I've observed is that when people first see Cypher, they sometimes get a little bit confused. So let me walk you through how Cypher thinks and how Cypher works. So basically it turns out that a really important operation in a graph database is pattern matching. It's not the only one, but it's probably the most important operation that you can do on a graph, right? So let's say that we want to match a very simple pattern. Basically what you do is that you describe a pattern, A loves B, and then you throw that to the graph database, and it's going to look inside its entire big graph and give you instances of A loves B, right? So conceptually very straightforward. But the question is, if you have a query language which sort of by its nature is textual, so two-dimensional or maybe one-dimensional actually, how do you describe a multi-dimensional structure, right? And the answer is obvious, I think, in hindsight. You use, wait for it, ASCII art. Hands up, how many in this room remember ASCII art? Half or so. So we're bringing it back. We're bringing it back to the mainstream. Finally, ASCII art, right? When I was in high school, a very popular thing was to pass around small calculators, TI-82 calculators, with ASCII art pictures of, let's call it, beautiful ladies. And we're bringing that back, but now we're using it for good, and we're using it to query graphs, right? So you can see here that in ASCII art, if you want to describe a node in ASCII art, one way of doing that is to wrap it in parentheses. You can see that A here sort of is a node. And then we want to describe a pattern where from A to B, you can see that we've drawn an arrow here using minus and then greater than, actually, I guess less than. And then we have another node called B. And then we can add the sort of, we wrap this in what we call a match clause, which instructs the graph database to match this pattern. And then we say that, look, we want to bind this to somewhere in the graph. So we want to just not find any A's that loves B's, but we want to find an A node which has a property called Adam, right? And the result of this is B, and we want to return B. So these are all the people or the things that Adam loves in this particular example. So going back then to the sushi restaurant example, we would start out with me, which is a friend of someone, who likes a restaurant, and that specific restaurant is located in New York, and the restaurant serves sushi. And then we bind those nodes down there into specific nodes in the graph, where me has a name Emil, and New York.location has location New York, etc. And we return this. This is a stolen example. It's stolen from a blog post by a gentleman called Max DeMarcy, who's one of my colleagues at NEO. And when Facebook launched Graph Search about, I guess, a year and a half now, they launched it midweek, and that weekend he hacked up basically Facebook Graph Search using Neo4j over a weekend. Not, of course, as scalable as Facebook, etc., but it's pretty cool that you can do that in a weekend using Cypher, some natural language parsing, etc. I definitely urge you guys to check out his blog. It includes a bunch of cool things, including this one. So what happens then from a runtime perspective, right? So we've described this pattern, and then on this huge graph, Neo4j is going to take that little pattern and it's going to find instances of it and return that back to the end user, right? So, okay, that's cool. That's a neat little language. But how does it work in the real world? So this is an example from the real world where actually a customer of ours had the following problem. They were modeling HR hierarchies. They were modeling, starting with the CEO, all of the CEO's direct reports, and the people reported to them, and then this huge hierarchy that is a company today, the company organization. At least in theory it's a hierarchy, but we all know that in reality it's a graph. And the question they wanted to answer was that given a specific individual, like, I don't know, the SVP sales, take that person, find all the people that they manage up to depth 3, so directly and indirectly, and how many people report to them. It's a pretty simple question, you might think, right? And their SQL code looked like this. And this is actually a lie. This is actually a simplification, because in reality, the real example that they were doing was up to depth 8. And when you get to depth 8, then that is kind of expensive. And it got so awkward for them to write that they ended up, they were never successful writing it, so they ended up writing a program that generated the code, actually. And in that way, they managed to construct the SQL that handle up to 8 levels down. But then, of course, once they ran it, it was just too slow. Yeah, so the question is, why was that such a cumbersome example? No, actually the real reason why it was so cumbersome is that it has variable path length queries, which are really, really awkward to express in SQL. There are some syntactic sugar around it. Connect by in Oracle sometimes works with with a number of constraints on it, but not one that works generically and well. In Cypher, however, this query looks like this, right? So pretty simple as an example. Okay, so that's cool, but what about performance then, right? So we've talked about expressiveness from a, let's call it, compile time perspective, right? Which is really important as a developer. But what about runtime performance, right? And so one example of this is when we were contacted a while back by a big social network that you've heard about. And they said, we've looked at all of NoSQL and we use a lot of it, but like graphs, come on, graph databases just expose exactly the abstractions that we want to work with. However, like the only thing we really care about is performance. So can you show us some benchmarks? And of course, benchmarks is the root of all evil or something like that. It's what is the saying? It's lies, damn lies, statistics, and then benchmarks, right? So we, being the honest geeks that we are, we said, hey, we can prove anything with benchmarks. So instead, how about you give us a scenario and we'll show us your numbers. And show you our numbers. And basically the scenario that they gave us was this one, right? So there's a small social graph with 1,000 people. We have 50 friends on average per person. And we grab 2 people on random and we check if there's a path between them, right? Not even how the path works, but if there's a path between them. And then we return that result. We've implemented that in MySQL. Actually, a MySQL consulting shop implemented that in MySQL with 1,000 people. I think you can see the schema in front of you. You have a person table, and then you have a friends table, right? And person table has ID and name, for example. And the friends table has ID and ID, right? ID 1, ID 2. And if person 3 is friends with person 7, you're going to have one row saying 3, 7. Right, and then another row saying 9, 13, etc. And you're going to end up doing a lot of self-joins in the second table. If you have 50 friends on average, it's going to end up being with 1,000 people 1,000 rows in the first table, that's 25,000 rows in the second table, and it's a 2,000 millisecond operation in MySQL. This comes back to the runtime cost of a bunch of joins, self-joins in the same table. In Neo4j, this is a 2 millisecond operation, which we feel super happy about, of course, but it's also kind of obvious, right? This is what we're supposed to be good at, right? This is graph data. This is where we're supposed to excel. So we upped the ante a little bit, and this is running on 2 laptops ago, my laptop 2 laptops ago, with a 300 megabyte heap. We added 1 million people, so 25 million connections in total. Grabbed 2 people at random to check to see if they're connected, and it's still a 2 millisecond operation, right? So pretty dramatic example of the type of performance benefits that you can get, not guaranteed to always get. Come on, the basics of NoSQL is that you choose a database that maps well to the data set at hand. That's what NoSQL is all about, right? And the era of the one-size-fits-all database is over. But if you have that type of data set and that type of workload, you can get these kinds of examples. Question?
Are you going to tell us what it is about a graph database like Neo4j that makes it so much more efficient?
Yeah, so the question is, am I going to talk about the internals and what is it that makes it so efficient? No, but there's a talk tomorrow at 8, which will go into some of this, at least. And you can hit me up afterwards, or Stefan. Can you wave, Stefan, who works in the Cypher team, and he'll be able to tell you a little bit more. So this is still slideware. I haven't shown you any running code of this. You shouldn't trust it, right? We have real customers that you can't see because I guess the slides are cutting off. But real customers experiencing this in real time. This is one example of that. This is eBay, which uses for their same-day delivery service, right? And they have some nice quotes about it. They used to have a situation, they were all on MySQL, and they do, basically, when you click on eBay, they do same-day deliveries, sometimes within the hour of when you buy something on eBay in selected cities, which is freakishly cool, right? This is basically the response to the Amazon drones, which are also very cool, but this one works today. And it's all based on Neo4j. They used to be on MySQL, and they had a situation where some of their slowest queries were slower than some of their fastest deliveries. So they had queries that took like 45 minutes, and some of their deliveries took 30 minutes, right? The physical delivery of the goods. That's when you know you're not in a good situation. They switched out to Neo4j and have response time in the milliseconds. All right, so that's the foreplay. So what about use cases then? Social, non-social graph use cases, right? So let me give you a snapshot examples of the type of breadth that we see today. The first one is network impact analysis, and I'm actually going to challenge the demo gods and show you this live without a mirrored screen. So this is going to be interesting. So when you install Neo4j, the first thing that you see when you fire up Neo4j is that you're going to see the so-called Neo4j browser, which is the web user interface for Neo4j, which is a super simple, very clean, minimalistic UI. It's basically a REPL. Hands up if you know what a REPL is. Some people, a redevelopment loop, right? So there's a bar at the top where you're going to end up typing in Cypher queries. Every Cypher query is going to give you a little window, if you will, a little frame with a search result that you can look at, that you can interoperate on, etc. To include some nifty little guides and a sample data set and things like that, right? So for example, I can do a super simple query. I can see what I'm typing right now. So let's see if I type something coherent. I did, but there's no response. So basically what I did now is I probably the most simple Cypher query, which is match any node and then return it. And we can see here that we don't have anything in the database yet. But I'm going to show you a network management example. If I can click. All right. So here we have some Cypher code using syntax that I haven't showed you yet. This is a create statement, which basically works the same way. You throw in a create there, and then you draw a graph using this ASCII art syntax, right? So here we're creating a bunch of nodes with a label resource. We create the CRM system, we create the database virtual machine, a server 1, server 2, etc. And then we're not happy with just creating the isolated nodes, but we also create the relationships between them. Specifically, only one type of relationship called depends on. So we want to match the dependencies in this sort of very, very trivial, very tiny data center, right? So we say that the CRM depends on the database virtual machine, etc., etc., etc. So if we run this and we do the same query as before, we're going to see, hopefully, most of you can see this. I may be able to. Oh, man. Yeah, that doesn't make it better. Okay. So what we see here is that we have the CRM application, which depends on the database virtual machine, which depends on which has a dependency also on the public website, or the other way around. The public website has also dependency on the database VM, which runs on server 2, which depends on the SAN. I don't know if you guys can see this, but hopefully conceptually you get this. So imagine that you're a big telco, or imagine that you run a web service operation. Then you would have a data center looking like this, but not with 7 nodes or whatever we have here. 7 nodes, but with 700,000 nodes or something like this, right? So we describe this, and now we can start running some very simple queries, right? So this query here creates it. I'm just randomly clicking around here. This query here checks the impact. What happens if server 1 goes down, right? So we take server 1, and we check all the the upstream dependencies of server 1. What happens if server 1 goes down? If we want to check all the direct dependencies, we just have this asterisk like this, right? Without an asterisk, and it's going to show you exactly that only the web server VM is depending on that one, right? But if we want to check all the transitive things, then it's as simple as adding a star like this, right? And we're going to see that on the web server VM, of course, the public website depends, right? So very simple, conceptually simple query, but very difficult to express in SQL and very easy in Cypher, at least if you can see the screen when you type. So there are a couple of other ones, but I think the coolest one is this one, which finds the most dependent upon component. Without geeking out too much, there's a concept in graph theory called centrality. And centrality basically describes how important a node is, right? So you can imagine that if you're a telco and you want to map influencers in your graph, who should I really try to upsell my new whatever phone or something like that in order to get that to spread through the social graph, then these are the 5 people that you should hit first. That's a centrality algorithm, right? And there's a bunch of different types of centrality, degree centrality, betweenness centrality, eigenvector centrality. They all have fancy schmancy names. This one is called, I think, this is going to end up being a betweenness centrality algorithm. But basically, it tells us that if we only have budget to replicate or implement fault tolerance for one of the devices in our network, which one should we do that with, right? And in this example, it comes back with, as a huge surprise, as absolutely no one who's run a data center, it's the SAN, because basically everything else depends on the SAN. So this is an example of network impact analysis. These were all trivial examples, but imagine this with 700,000 nodes, right? And yesterday we had a situation where maybe an average data center had 1,000 of physical machines or something like that, right? And maybe they were connected squared with that. So like, let's say 1 million connections between them, which is big, but not impossible to manage. Today, and for some definition of yesterday and today, right? Today, an average may be 100,000 physical machines. And not only that, every one of these physical machines runs 10 virtual machines. So that's 1 million already there. And imagine this, times square, Metcalfe's law, the explosion of connections between all of them makes it really, really difficult to keep track of. So this is a very popular example of graph databases today. Check the impact of something happening on a network. Another example, this actually comes a little bit back to the roots. This is route finding or route finding, depending on where you're from. But basically, if I want to get to point A to point B, and this example I think is the London Tube map, how do I do that most efficiently, right? So imagine that every city in the US is a node, and all the roads connecting them are relationships, and I want to find out how to go from point A to point B. How do I do that, right? So there's, without revealing too much, all of the at least 1/3 of all the flight paths in the world actually will be calculating using Neo4j in the near future, let's say. So imagine that you're doing price optimization for flights, right? That thing that we're all battling with when we're trying to get from point A to point B, right? That describes all of the nodes in that world is all of the airports, and the relationships are like all the flight routes from point A to point B. And then when you want to optimize how to get from San Francisco to Copenhagen, right? There's a multitude of ways you can get from point A to point B, and you need a graph algorithm to figure that out. Recommendations. It turns out that ever since we started moving from physical to online retail, there's been an increasing demand on recommendations. And Amazon probably started this, at least in the mainstream. And forever in the physical world, retail outlets have stored physical records, or not physical records, but purchase records of the transactions, the e-commerce transactions that are happening, right? But it turns out that when you look at that data as a very isolated set of elements, it's very difficult to do anything with it. But if you see that, let's take this purchase information and say that there's an individual called Emil, because that's the individual is in that purchase record, and he has bought a camera, and he's bought milk, and he's bought an Xbox or something like that. And then there's an individual called Adam, right? And he's bought the same things, but there's one fourth item that Adam has bought that Emil hasn't bought, right? And then there's a very trivial graph algorithm called open triangle recommendation or collaborative filtering, where you can implement that. It's 1 or 2 lines of Cypher, which is going to identify this fourth thing that Adam had bought that Emil hadn't, and then recommend that to him. This is trivial to do in a graph database, but it's 1, 2, 3, 4, 5, something like that joins in a relational database. And in reality, what you want to do is much more sophisticated than that. Because one of the items that Emil bought was a book. It was The Two Towers by J.R.R. Tolkien. But you don't want to do recommendations based on that specific book. But in reality, that book is part of a category called fantasy books, which is part of a category called, sci-fi books or something like that, right? And you want to do recommendations based on that abstraction, not on that specific element. And that alone leads to an explosion of joins in this particular example. So Walmart is now publicly using Neo4j to power their online recommendations, not their in-store recommendations, but all of their online recommendations are powered by Neo4j. Logistics. We were contacted by one of the biggest package couriers on the planet a while ago, and when they said that they basically handle all of the package routing or parcel routing, so not TCP/IP packets, but actual those physical package, for a major country in Europe, and they said that, we're running into trouble because we see that 2 years from now, we're not going to be able to handle the peak volume. And peak volume in this business, it's a very seasonal business. So peak volume is, of course, Christmas time. So basically they saw that, okay, so we manage all of the parcel routing for this major country, and they're not going to get their Christmas gifts in a couple of years. And as they tried to debug why, they tried to figure out, is it a physical infrastructure problem? And the problem wasn't with that. The physical infrastructure in that country is very good. There's a lot of very big highways in that country, let's say. But the problem was that their software that backed all of the logistics and all of the getting from point A to point B intelligence could not use lateral connections. They could only describe a connection into a hierarchy. So if you're sending something from, let's use a local example, from San Francisco to Menlo Park, I don't know how many of you are local to the Bay Area, but that's 30 miles or something like that, then you had to send it to a core distribution center first. You might have to send it to Chicago or something like that. Even though there's a physical way of getting from San Francisco to Menlo Park, it's just one highway away, right? And so they ended up replacing their entire relational database backend and swapping in Neo4j, and it's been up and running now for a year, I believe. It's been routing 100,000 parcels per minute at peak load, which is pretty significant. It's a very cool, just from a implementation perspective, it's a very cool example because physically you have a chute where these packages drop down and they're going to scan the barcode at the top of that chute, and then at the end, as gravity has pulled that package down, a few milliseconds later, you're going to have to make a choice, either left into that truck or right into that truck. And so you have a couple of milliseconds, and they're going to throw that query to a cluster of Neo4j instances that within a couple of milliseconds calculates the optimal route, and then decides either left or right into whichever truck. One example, access control. Actually, the earliest example of graph databases that I know of. This is the origin of why we ended up building Neo4j in the first place. So access control very typically involves users connected to some kind of content. And if it only were that easy, we could use just a relational database saying Emil has write access to this particular file. But users are organized in groups. Groups sometimes belong to multiple groups. You're no longer just a member of a specific part of the organization. And this particular file is not just an isolated file, but it belongs to a folder, and that folder belongs to a folder. And you can see how that builds up a big network as you connect these two different trees to one another using access control lists. This example inside of finance is called entitlement. And we have a few of the biggest investment bankers using graph databases for this today. So basically the problem is, as they onboard a new trader, it used to take them 2 weeks before that trader was up and running. And because it just took that long to resolve all of the different assets that they had access to. And now it's a millisecond operation to parse that entire thing. So that's access control. Fraud detection is another example where it has previously been using mainly correlation analysis, which looks something like this, right? So you have a situation where you're mapping two different things, right? For example, total dollar amount and transaction count or something like that, right? And you see that normally in the mainstream we have a band here where within this range things are okay, things are normal. This is how it's supposed to be, right? And then we look at outliers. Hey, whoa, someone is outside of this normal range. And then we're going to investigate that one. And this has been very popular and is still used today very much so. Maybe the foundation of fraud detection inside at least certain industries. But fraudsters are becoming much more sophisticated. And what this misses, if you stay inside of this band of normality, but you do, for example, a fraud ring. So you have every single individual has behaved within normality. But together they form a fraud ring. This is impossible to detect using simple correlation analysis. Taking a connected data view will allow you to do that. I could go on, and I will if you hit me up afterwards and ask me about more use cases. But basically the summary is this. Graph all the things. Every vertical, every use case, graph them. No, not quite, but pretty close. So most of you know Gartner, the #1 analyst firm on the planet today, probably. And they did something unusual a while back, where they said that, hey, let's take a look at the consumer web, and let's try to analyze that. And they're mostly focused on the enterprise. But they said that you can actually understand all of the dynamics of the consumer web. So we're talking about the Apples and the Googles and the Facebooks of the world, by looking at it through the lens of there are 5 key resources that all of these big giants are battling over. And they wrote a really cool paper called The 4 Giants and the 5 Graphs of the Consumer Web. Right? And they said that these 5 key assets are the social graph, the interest graph, the intent graph, the mobile graph, and the payment graph. And if you can conquer these and you can own these, that is a huge amount of value in the consumer web. So we looked at that and we thought it was very cool, of course, being graph guys. And we said, hey, let's take this and start mapping other verticals. So we started doing that, and I'm going to end with a little bit of a flavor of that, and then we're going to move on to Q&A. But basically, we've started to explore different verticals and find the 5 graphs of that vertical. And in Telco is one of the first that we mapped. We've found these 5 graphs that seem to be common amongst all the telco customers and community users that we see. The network graph is the graph that we talked about before, with the resources being cell phone towers, switches, routers, firewalls, etc. We have the social graphs, which is good for influence analysis, which I alluded to a little bit before. The call graph is actually an inferred social graph based on the CDR, the call data records. The master graph ends up actually being very, very popular inside of telco. So the so-called master data is all the data that is non-transactional in an enterprise. So all the customers, all the organization with the employees and the supply chain, all of those things ends up being a lot of graphy data. And then the help desk graph actually ends up also being very, very popular. All of the support cases that people file and how they relate to one another and to issues and to tickets that supported them and to the various specific products, but also the parts of those products that the support cases adhere to. 5 graphs of finance. I'm not going to go through these in detail. If you're in a specific vertical and you want to know more, please come up and ask me afterwards. And if you're in a vertical that I'm not showing here, the final vertical is the 5 graphs of healthcare, and you have some ideas around what you believe are the key graph in your vertical, please hit me up afterwards, because we're super interested in mapping these things out. So to conclude, if you think that this sounds interesting, that graph databases aren't just good for social, I'll get to it in a minute, then there's a book out there called Creatively Graph Databases. It's an O'Reilly book. It's pretty good. It's a fantastic introduction. It's available for free as a PDF on graphdatabases.com. So that's a great next step if you want to learn more about this. An even better next step for those of you who are local, it's going to be super easy, and if not, it's a good thing to travel for. There's an upcoming conference called Graph Connect, which is the biggest conference related to graph databases and graph database applications. It's a one-day conference. It's at the SF Jazz Center here in San Francisco, and there's going to be a lot of interesting speakers from ConocoPhillips talking about oil mining and how that relates to graph databases, to eBay, to many of the examples that I had only time to talk about for a minute here. They're going to go into really core detail. There's a huge discount for Java 1 attendees, at least for the next week or two. So use that one called Java 1. And on that note, I want to wrap it up. And my final urging is, if you thought this was interesting, there's the book, of course, there's the conference. But let's not forget that Neo4j is open source, and it's available free of charge. For any of you who think this sounded interesting, please go to neo4j.com and download it and add some data and start graph things. Thank you very much. Me off. Can you turn me on? Yeah, so we have time for a few questions. So, you had a question? Yeah. So the question was, can I talk about how to use master data in graph? Yeah, in the generic case, absolutely. So it turns out that in master data, there's a lot of hierarchies and a lot of graphs, right? So one type of master data, organizational MDM, right, has an org tree as the foundation. Org tree, of course, is a big graph. One of our earliest Fortune 500 customers was Cisco. They're now public as being a Neo4j user in their MDM division. And they used us basically for sales compensation calculations. So imagine that you're Cisco, so you have 4 gazillion sales reps, right? And they're organized not just in like an organizational hierarchy, but they also map to a territory. And they map to different users. Right, and when you translate and you want to do Salesforce compensation, that's a lot of connected data that you need to traverse. So those are some examples of master data. Any other questions? Go for it.
Could you talk a little about how well Neo4j scales?
So the question is, can I talk a little bit about how well Neo4j scales? How well Neo4j scales? Would love to. So basically, the scale-out model of Neo4j is master-slave replication. So think MySQL, right? So you have a single master at all times, and then all of that data is being replicated to all of the slaves. It is a little bit dissimilar from MySQL in that the master can get re-elected, so it's not fixed to be a specific master. And you can actually write to the slaves, unlike in MySQL where you don't write to the slaves in MySQL. That's going to really mess you up. So that's the foundation for the scale out. So it's replicated scale out, which gives you a number of advantages. It gives you read scalability. In particular, it gives you fault tolerance. What it won't give you is write scalability, right? So you're still going to be bottlenecked by the write throughput of the single master, and it's not going to give you sharding. And sharding is actually not a goal in and of itself, but a means to an end. And the real end when it comes to sharding is to achieve write throughput and write scalability. So that's sort of the drawback with the Neo4j scale-out model as it is today. It won't give you write throughput, but it will give you read scalability. On the write throughput, actually the stuff we're working on right now, Neo4j 2.2 and 2.3, will increase write throughput by at least 1 order of magnitude. Cool. Final question.
I understand the performance on correlation but if you have a use case where there's large documents in nodes, is it a good use case? Because we're always anticipating the human document database and I graph one. And my use case is in media where correlation is important and bundles
Yeah, that's a great question. So let's say that you have a use case which is very document heavy, and you could look at that use case and say that, hey, this is all graphs, right? Because actually the graph model is the mathematical superset of the document model. If you draw documents to its logical extent, the long arc of documents and the long arc of graphs, there's no need for documents. There's not a single use case that document databases can do that graphs cannot do. At the long arc of it, like at its full power. We're not there yet today. So today, it's going to come down to very specific, sorry, this is like a huge consulting answer, but it's also a true answer, which is it's going to depend on your use case. Like, our ambition is that over time, we should be able to handle all the richness of everything that a document database can do. But today, we're not there yet. So if you have a situation where you have super deep documents with a lot of content, I would be down. Maybe you can put it in Neo4j, maybe you can't. I would at least look into that and do real performance benchmarks on it. But over time, that's definitely our ambition to be able to handle anything that a document database can handle. And those of you, I'm sure many of you have used document databases because they're by far the most popular of the NoSQL databases, right? And there's a bunch of times when, like, inside of the documents, you end up encoding basically foreign keys. You have, like, you encode a key element that refers to a document over here, right? And then, except it's not a real foreign key. There's no support for that in the model, right? So then if this thing gets deleted, you point to what? To null, basically, right? So there's no abstraction to really support that in the model. So logically, those models are a graph, right? And that's what the graph model is there for. Today, we're much better at the relationship fast traversing than we are at handling, let's say, a completely disconnected document space, right? Just a data set with just documents without any connections. That's not our forte. Over time, it's definitely our ambition that we will be. And next year, if you ask me the same question, the answer is going to be a little bit better, and then a little bit better, and then a little bit better. But today, I would say it's very much depends on your data set. And with that very consulting-oriented answer, I'm going to wrap up. Thank you very much for paying attention, and if you have any more questions, please come up and ask me afterwards.